Section 6.3, Systems of Linear Equations, Augmented Matrices. Part 1, Matrices in Row Echelon Form. A matrix is a rectangular array of real numbers enclosed with square brackets. A matrix is said to be of size m by n if it has m rows and n columns. Let's determine the size of each of the following matrices. So the size is the number of rows by the number of columns. So this first matrix has 3 rows and 2 columns. So it is a 3 by 2 matrix. The second one, we have 2 rows and 2 columns. So that is a 2 by 2 matrix. And the third one, we have 2 rows here and 3 columns. So it is a 2 by 3 matrix. Now I also just want to say that sometimes people write matrices in big parentheses instead of the square brackets. That just is another way to write the matrices. Either way is acceptable. Definition: a matrix is said to be in row echelon form, provided each of the following conditions hold. Number 1, the first non-zero entry in each row is 1. We refer to that as the leading one. Number 2, the leading one of a given row is to the right of the leading one in any row above it. And number 3, a row of all zeros is below all rows with any non-zero entries. Determine which of the following matrices are in row echelon form. So we'll check for each matrix these 3 conditions. If they all hold, then it is in row echelon form. So number 1, the first non-zero entry in each row is 1. So this first row, the first non-zero entry is a 1. The second row, the first non-zero entry is a 1. And the third row is all zeros. Number 2, the leading one of any given row is to the right of the leading one in a row above it. So this right here is a leading one of row 2, and that one is to the right of the leading one in the row above it. So that condition holds. And condition 3, a row of all zeros is below all rows with any non-zero entries. That is also true. The row of all zeros is at the end. So this one is in row echelon form. The second matrix, the first non-zero entry in each row is 1. The first row, the first non-zero entry is 1, but the second row, the first entry that's not 0 is 2, not 1. So this one is not in row echelon form. For the third matrix, the first non-zero entry in each row is 1. In this row, the first number that's not a 0 is 1. Same with this one. The first number that's not a 0 is 1. Condition 2, the leading one of a given row is to the right of the leading one in the row above it. So here's the leading one in row 2, here's the leading one in row 1, and the one in row 2 is to the right of the leading one above it. And condition 3, a row of all zeros is at the end. There are no rows of all zeros, so that doesn't matter. This one is in row echelon form. The next matrix, notice these are the leading ones in row 2 and 3, but the leading one in row 3 is not to the right of the leading one in the row above it. So this one is not in row echelon form. And the last one doesn't meet the third condition. The row of all zeros is not at the end. So that one is also not in row echelon form. A matrix is said to be in reduced row echelon form, provided both of the following conditions hold. So first, the matrix is in row echelon form. And second, the leading ones are the only non-zero entries in their respective columns. So these are the same matrices. The first condition here is the matrix has to be in row echelon form. So these 3 were not in row echelon form, so we know they can't be in reduced row echelon form because that's the first condition for reduced row echelon form. The second condition, the leading ones are the only non-zero entries in their respective columns. If I look at this first matrix, here's the leading one, and that is the only non-zero entry in that first column. We just have 1, 0, 0. The next row, here's the leading one, but that is not the only non-zero entry in that column. There's a 6 in that column also. So this one is not reduced row echelon form. It is in row echelon form, but not reduced row echelon form. That other matrix that we said was in row echelon form, the leading ones are the only non-zero entries in their respective columns. Let's check that. So here's the leading one, and in that column we have 1, 0. So that is the only non-zero entry in that column. This is the leading one of row 2, but in that column, it's the only non-zero entry also. So this one is in reduced row echelon form. So how does the matrix work with a system of equations? If I want to write a system of linear equations as an augmented matrix, what that means is I'm going to write the system of equations, but with just the coefficients, not the variables, not the plus and minus or equal sign. So the first row will be a 2, -2, 1, and 4. And I can write that, I can draw that vertical line if you want to represent the equal sign and to show this is an augmented matrix. So the left side are the coefficients, the right side are the constants that are on the other side of the equal sign. So the middle row now will be 1, -3, 2, 1, and that comes from this equation right here. And then the last row, we have 1x, 1y, 0z equals 3. So I've written this system of equations as an augmented matrix. The following matrix is in reduced or echelon form. Determine the solution of the system of equations. Well, let's translate each row into an equation. So if this is x, y, and z, and then this is the equal sign, then the first row says 1x plus 0y plus 0z equals 2. The second row says 0x plus 1y plus 0z equals -1. And the third row says 0x plus 0y plus 1z equals 3. So the solution is the point 2, -1, 3. Notice that this matrix is in reduced or echelon form. So if the matrix is in reduced or echelon form, then the 2, -1, 3, that last column, is your solution to the system of equations. Let's look at this one. Again, we're going to translate each row into an equation. So the first row says 1x plus 0y plus 0z equals 2. The third row says 0x plus 1y plus 5z equals -1. And the third row says 0x plus 0y plus 0z equals 3. Notice that last equation is impossible because 0 will never be 3. So this has no solution. The system of equations, no solution. Let's try this one more. Again, we're going to translate this into equations. So the first row says 1x plus 0y plus 3z equals 2. The next row says 0x plus 1y plus 5z equals -1. And the last row says 0x plus 0y plus 0z equals 0. Now that last equation, that's always true. No matter what x, y, and z are, 0 always equals 0. So that isn't particularly helpful. This is a dependent system of equations because we only have really 2 equations, but we have 3 unknowns. So if I want to write the solution in terms of z, then the first equation, I will solve for x, and I get x equals 2 minus 3z. So now x is in terms of z. And the second equation, I can solve for y, and I get y equals -1 minus 5z. So now y is in terms of z with no x in there. So my solution as an ordered triple will be 2 minus 3z, -1 minus 5z, z. And there is the solution to this system of equations.